And now I apologize with the next speaker for even adding one further question. But now it's time to give the microphone, let's say, to Wasiur, which is going to talk to us about dynamic survival analysis. I know a little bit about survival analysis, I know a little bit about survival prediction, but I don't know what dynamic survival analysis is. And so I'm looking forward to your presentation. So thanks a lot for giving us the opportunity to hear your research. Thank you very much.
Thank you so much for the opportunity. So yeah, if you already know survival analysis and if you know a little bit of dynamical systems theory, then you are in the right place, because what I'm going to do is to marry these two things together, which hopefully it'll end up being a successful marriage. So yeah, my name is Wasiur KhudaBukhsh. I'm a postdoctoral scholar at the Mathematical Biosciences Institute at the Ohio State University. And I'm going to talk about dynamic survival analysis and how COVID-19 shaped it. So let me begin with a brief overview of, and some of the stuff that I'm going to talk about might be a repetition and might be too naive to begin with, but I think it's important. So what I'm going to give you is a brief overview of epidemiological models. So when we talk about epidemiological models, there are two distinct classes of models. So on one hand, you have ecological models. So these are your population level models. You try to describe the time evolution of the count of susceptibles and the count of infected and so on. And on the other hand, you have a micro scale approach, which are the agent-based models. So here, as opposed to ecological models, you don't try to describe the dynamics at the population level, but rather at the individual level. And dynamic survival analysis is somewhere in between, in the sense that it creates a bridge between these two types of models. So if there is going to be a single takeaway from this talk, it is perhaps this statement that a dynamic survival analysis basically creates an agent-based model out of an ecological model. So it takes a population level model and gives you an agent-based model. The other way is actually quite simple if you think about it. If you have an agent-based model, you can just sum things up and you end up getting a population level model. So that's quite trivial, but DSA does the opposite thing. So hopefully it will be a bit more clear as we go on. So a bit of historical context. So in the sense, I mean, it's probably not history yet, but hopefully at some point it will become history. So back in March 2020, when the Ohio State University Infectious Disease Institute COVID-19 response modeling team was formed, and I became a part of it. And the team was formed with a particular task as requested by the state government. So, and the task was to predict statewide case counts and hospital burden of COVID-19. So pretty similar to, I think, many people did the same thing for their respective state governments. And I'm coming from the perspective of from Ohio, basically. So, and what you see here is on x-axis, you have the dates. So as you can see, this is early March. And the new cases, I mean, these are still below 100, so nothing to worry about, but we wanted to be proactive. And this is the kind of prediction that we gave at that point. So just to highlight to the politicians that if we do interventions, then we might end up getting smaller number of cases, so which are shown in blue here. But if we don't, then it will be it will infect many more cases, and then these are the yellow regions are the scenarios without mitigation. And this was primarily to basically highlight the need for mitigation strategies, and share a few pictures of our Governor DeWine and Dr. Amy Akin, who was the director of the Ohio Department of Health back then, kind of like the health minister, showing our model to the press and requesting the public to stick to these measures and socially distance and so on. So that's the context, but we also did more than that, just producing these scenarios. We actually produced these predictions of hospital burden in different healthcare catchment areas in the state of Ohio. So this is a map of Ohio, and the different hospital or healthcare catchment areas are shown in these different colors with their predictions. And we also help with the PPE requirements almost throughout the year. And we continue to do so. But now let me try and explain the underlying mathematics a little bit. And for that, I'll choose the simplest possible model that's out there. So that's a Markovian mass action SIR model, so which has kind of become a household model these days, thanks to the pandemic. So let's start at the micro scale. So we try and build an agent-based description. So suppose there are n susceptible individuals and m infected individuals initially. And for each of those individuals, we define some indicator function, some stochastic processes that keep track of their immunological status. So SI is 1 if he or she is still susceptible at time t, and 0 otherwise. And we'd also define II and RI in more or less similar fashion. And for simplicity, we just assume a Markov model, meaning that we just have 2 parameters here, the infection rate, beta, and the recovery rate, gamma. So how do we simulate trajectories? So one way to simulate trajectories is to use the selfie construction. So I'll briefly describe how this works. So in the selfie construction, what you do for each of those individuals, you assign a threshold, which is distributed according to an exponential distribution with mean 1. And then you keep track of the cumulative infection pressure, which is nothing but the integral of, this is the rate, and this is the total number of infected individuals at any given point in time. So you're basically integrating rate times the scaled number of infected individuals. You keep track of this this stochastic process, this quantity, and then you compare. So what you do is you compare the thresholds with this cumulative infection pressure, and then you say that a susceptible person gets infected whenever the cumulative infection pressure crosses his or her threshold. So pictorially, this looks something like this. So suppose we start with a single infected individual. So the slope of my cumulative infection pressure is just beta over n at the moment. So on x-axis, we have x, time. On y-axis, I have the ordered thresholds, so starting from the smallest here, going up to the largest thresholds, which are all exponentially distributed with mean 1. And the green curve is the cumulative infection pressure. So I have slope beta over n, so it's going up, up, up. And here it crosses the first threshold, so one more person gets infected. Now the threshold, the slope is 2, beta over n, so it increases, it goes up. Here somebody recovers, so we're back to beta over n. And then it crosses the second threshold, so it goes up, somebody recovers, it goes up here, and then there's the third threshold, somebody goes up, there's one more recovery, there's one more recovery, and now everybody has recovered and there are no more infected individuals. So all other susceptible individuals basically escape infection, and this just becomes flat. So that's the algorithmic part of selfie construction. Mathematically, what this tells us is that if I pick a random susceptible individual, and then I try to calculate the probability that he will remain susceptible till time t. So this is called the survival probability in statistics. Given the history of the process, then that probability is simply e to the power minus the cumulative infection pressure. So that's the bottom line of the selfie construction. The survival probability, the probability that a susceptible individual will remain susceptible till time t, is just e to the power minus this. Okay, so that's all of the micro scale analysis. We know how to simulate trajectories. We know the underlying probability distributions. Let's now move from the micro scale to the macro scale. Now, at the macro scale, as I mentioned, we no longer keep track of individual trajectories, but rather population level counts. So if I have counts of susceptible individuals, so counts of infected and counts of recovered individuals, and if I scale it by the initial number of susceptibles here, and then one can show that this process, it's also a Markov process, will actually converge to deterministic functions that satisfy a system of ordinary differential equations, which is shown here. And you might have immediately recognized that this is the same set of equations that are known as the Kermit-McKendrick system of ODEs for SIR model. On the right side panel, what I've done is I have the same system, but I have now partially solved the system. And there's a purpose why I did that. If we look at the ST function, which is the scaled proportion of susceptibles in the limit, so yeah, a population level quantity, this is nothing but e to the power minus beta times this quantity. But if you look closely, that this is nothing but the integral of this is nothing but the limit of n going to infinity, my cumulative infection pressure. So this ST, even though it keeps track of counts, scaled counts, this is nothing but in the limit a survival probability, thanks to the Selke interpretation. Now, if this is the survival function, then minus ST dot is a density, and e to the power minus this quantity is the scale density of an exponential function distribution. So this is nothing but a convolution of two densities. So in a sense, this is also a density. So this quantity IT, which is the scaled proportion of infected individuals, can be interpreted as a density function. And then this is nothing but a cumulative hazard function. So from the counting process perspective, we have a completely different perspective, because now we can interpret them as probabilistic quantities. And of course, because of this convergence, we know that this actually converges to this. So that's why we have this. So basically here's again a pictorial summary of this, whatever I just explained, that if I have these trajectories, S, I, and R, I can treat the S curve as a survival function. I can treat the I curve as a density, and the R curve as cumulative hazard function. So what happens if I draw random samples from this survival function? So this, if I do that, then I'll get the time to infection for an initially susceptible individual, right? So that's an individual level quantity, and I'm getting it from a population level model. So what basically, again, going back to the same interpretation, what DSA did, the dynamic survival analysis did, it took an ecological model and gave you an agent-based model. So out of the population level SIR model, it gave you probability distributions with which you can generate individual level trajectories. And not only that, it also gave you a likelihood function for free, which we can use for parameter inference. And that's the likelihood function that we used for the state of Ohio. It has a number of statistical benefits. The first benefit is that it's very simple, and it's a product from likelihood function, because of mean field independence, we can actually write down the likelihood function in terms of transfer times as opposed to population counts, because we no longer keep track of the entire population. We just need infection times for some random number of a sample of individuals. And the size of the susceptible compartment is not needed. So you don't have to make ad hoc assumptions that the entire city is susceptible or the entire country is susceptible. And moreover, you can actually estimate the effective population size for free out of this thing. And this works even if your transfer times, meaning the infection times and the recovery times, are censored, truncated, or aggregated over space and time. So because the entire toolkit of survival analysis is now made available to your dynamical system. So that's the mass action setup, but mass action models are not always justified, because in reality, things are maybe working more like a network model. So I would argue that a network-based approach is more realistic and sometimes more flexible, because you can easily incorporate social distancing, heterogeneity, and so on. So I'll quickly explain how to extend it to the network setting. For that, I'll so how am I doing with time? How much time do I have?
Well, I think you started 5 minutes later, so you can keep going for those extra minutes.
Okay, yeah, thank you. So yeah, let me quickly explain how to do the SIR model on network. So I'm going to take a configuration model random graph, and here's how the process evolves on the graph. So the red vertices are the infected ones, the blue ones are susceptible and the green ones are removed. And as you can see that we are also allowing dropping of edges. For instance, this edge disappeared. So this is to mirror social distancing. And the red vertices, they try and infect their neighbors, and then they recover after an exponential amount of time. So that's the bottom line. What are the key ingredients? The key ingredients are basically the degree distribution. So you have to specify a probability distribution for the degrees, and then the infection rate as before, recovery rate as before, and a delta parameter for dropping of edges. So that's to mirror social distancing. Once we do that, we can use marginal techniques to study the large graph limit of this process, as we did with the standard model before, mass action model before. And for the case of Poisson distribution, I mean, it also works for other distributions. It's just that the equations look a little bit clumsier. So I've chosen the Poisson case here. So for the case of Poisson distribution, you can describe the proportion, the limiting proportion of susceptibles using this ordinary differential equation here. And these are the revised parameters. I need to revise it because to avoid some identifiability issues. But the bottom line is you get a single equation for the limiting proportion of susceptibles for the SIR model on a configuration model random graph. Once we get that, we know that we can now apply our dynamic survival analysis approach. I can treat this susceptible curve as a survival function if I have scaled it appropriately, meaning that it starts at 1 and it goes to 0 in the limit, or even if it doesn't go, then I can rescale and make it a proper survival function. But if I do that, then I can treat it as a probabilistic quantity, namely a survival function, and write down the likelihood function and do the parameter inference. So that's exactly the likelihood function that went into our efforts, COVID-19 response modeling efforts for the state of Ohio. And I'll probably stop here and take your questions. So thank you so much.
Okay, let's thank the speaker for the great talk. And so, of course, are there any questions or comments? So I have a question about like so more complicated compartmental models. Are there any results on that?
Yeah. Yeah, that's a good question. So I didn't show you the other slides here. So for instance, if you want to study the dynamics in prisons and things like that, then a standard SIR model is probably not realistic. So you can introduce more compartments. You can actually introduce more covariates, age, sex, geographic location, and all sorts of things. But the basic idea still remains. Even if you have a non-Markov dynamics, I actually didn't talk about it. Even if it's not Markovian, you can still do it, because the whole idea of DSA is to take the dynamical systems and scale it appropriately, construct a Selke construction that's appropriate for the model, so that you can treat or interpret your dynamical system as probabilistic quantities. So you can do that for any number of compartments, or whether or not it's Markovian. It's just that you have to change your perspective so that you get these likelihood functions directly out of your dynamical system. So it does work.
So let me ask a follow-up question, which may be not making too much sense. Is there some infinity visibility property which turns out to be useful in your analysis? Because I know you mentioned the Poisson distribution, but is there something related to that which comes into play or not?
So the reason I chose Poisson distribution is one, the equation is the simplest for Poisson distribution. I mean, it would be even simpler if you have a regular distribution, so then fixed degree, but that's not realistic. And Poisson seems to be a good compromise between more complicated distributions or more realistic distributions and the simplest possible case. But the method works for any distribution, basically, as long as it has finite second moment. And the other reason, I mean, apart from the simplicity, is that we were also able to prove that if your degree distribution is Poisson type, meaning if it's binomial, Poisson, negative binomial, or regular, and only for these 4 cases, then the pairwise approximations that motivated from standard mean field theory of statistical physics, those equations are exact. So they become asymptotically exact. The equations they would match up. So, but only for these equations. So we thought, okay, it seems to be good. And for other distributions, the standard mean field equations are not correct.
Well, thanks a lot. Thanks a lot for your great introduction. Let's thank the speaker again. We can do it in two ways. One with the claps option, and also with our hands.
Thank you so much. Thank you so much.